Okay, can you hear me now? Yes. Great. Okay. Yeah, sorry. There's a switch on my microphone, which overnight probably one of my cats had trod on and turned the microphone off. Okay, right. So just to start again then. So at the end of the last session, we talked about field effect transistors, and we looked at their scale and their size, and we noticed that as time goes on, from 1993 up to, well, reasonably close to the current day, I updated this 2018, then got a bit bored with it, we're getting very, very large numbers of transistors, and this is something called Moore's law, where scaling effects come into play, and things just get smaller and smaller as time goes on. Obviously, we're going to get to a limit, and the limit will be when eventually the smallest size is about the size of an atom, and we're not that far away from that now. So we have to think of other things, other ways of improving our chip performance. And the current idea is to actually just put more and more cores or processing nodes on a single chip, and then run lots of things in parallel. And this leads us to graphical processing units where there are hundreds of little processors all doing very specialized things, but doing it all in parallel, which speeds things up a bit. It doesn't use more silicon because everything's smaller now. That's the point. Look at the size of these things here. These are equivalent functional units as time has gone on. So no, it doesn't increase the cost. You get more performance per square millimeter because you make things smaller. Eventually, of course, yes, you'll get to that. When you get to the point where you can't make the transistors any smaller, then bits of the area goes up. But you've got to go up a large area to get from here to here, and people could afford this. So anyway, who really needs that level of performance? That's the argument. It's a marketing thing now more than anything. Okay, so this is all led about by transistors. We've done bipolar transistors, but digital circuits are all done with switches, and field effect transistors are more efficient for that kind of performance. So they're the things that lead to the small scale. So wouldn't it be interesting to see if we can actually do analog circuits in field effect transistors, and that will lead us to this idea that we can actually then combine analog and digital circuits all on the same chip. And that's what drove a lot of this in the early days. Nowadays we can actually combine processes a little bit more if we want to. It does add to the cost a little bit, but it depends if you want performance. It's always a trade-off between cost and performance. But anyway, we need to look at these field effect transistors and see how they work, and then we can compare them with the bipolar transistors and understand a bit about how they operate and where we can use them. So the junction field effect transistor, the JFET, is an easy thing to understand, well, easier than a MOSFET. So we'll look at that because it's a nice development on from a bipolar transistor, even though it was actually invented before the bipolar transistor. And that will lead us on to metal oxide semiconductors, or MOSFETs, which we can talk about in a bit more detail. And these are more standard sort of logic switches, and we can convert those and make some quite nice linear amplifiers out of those, which is quite a neat little trick. So field effect transistor operation in both the JFET, the junction field effect transistor, and the MOSFET, operation is basically the same. It's similar to a bipolar transistor but not identical. So the number of carriers, so electrons or holes or whatever, in a conducting channel is controlled by a lateral gate. The details of operation are different in both these cases, of the JFET and the MOSFET, but whereas the bipolar transistor we were considering as a controllable current source, we can sort of think of these types of transistors as effectively sort of variable resistors up to a point. It's all both sides of the same coin in many ways. Excuse me. So the generic FET, so the operating principles of any kind of FET, be it a MOSFET or JFET, is sort of described by this type of idea really. We've got a piece of semiconductor. It doesn't matter if it's a P or an N at the moment. We can make both types. And we have connections at both ends of that bit of silicon, and we will call these S for source and D for drain. It's historical names. I didn't choose them. And then we So we're going to have current flowing through this device. Let me pull up a pen. So current, let's say it flows through here. And obviously the amount of current flowing through here is going to depend on the parameters in this material, how big it is, what it's made of, that kind of stuff. And if we then apply a field to this surface here, we can start to influence what's going on in here and change the current flow. What we actually do is we effectively reduce the width of this channel by applying an electric field on here, which pulls out all the sort of spare electrons in here, and it makes this much narrower. And if you make this narrower, then it obviously increases its resistance to flow. So we've changed the amount of current to effectively turn this into a variable resistor. So that's the sort of idea behind this kind of idea. So how could we possibly make one of these things? Let's consider some doped silicon. It has a resistivity dependent on various parameters in the device itself, and its resistance depends on these parameters and how long it is, really. If we now add another piece of opposed doped silicon, we have an elongated PN junction. So here's a PN junction, and we saw this excuse me, in the construction of the bipolar transistor. And when we had another piece of P over here to make a PNP transistor. So we can take this PN junction. What did I say on the other one then? What do I mean by this? I don't know. But what we're going to do is we're going to take two bits of silicon and join them together and see how we can make a JFET. So this would be the construction of a normal PN type diode. We've got a bit of P, a bit of N, and we've got wires going through the middle of it. What we can do is elongate these bits of silicon down. So we've taken our diode. So we know what happens in a diode. We've got this junction thing going on here, and we know that there's a depletion zone potentially in here if we reverse bias it, or there's conduction if we forward bias it. So we extend that down a bit like that, make it look like that. So we've got this sort of very fat, short diode now. And then we can shrink this bit down here if we wanted an N-channel type device. And then we actually just conduct through it. So if you think of it as conducting through a diode this way, that's what a field effect transistor is. So it's a diode, but conducting through the wrong way, if you like. That's one way of visualizing it. And then we can control the flow by applying a voltage here. So if we take this device and we connect it like this at the moment, so it's both connected to ground, so it's a bit pointless in many ways, but it helps us to understand hopefully what's going on. So we connected it up like this, and we apply a negative voltage to this P-type here. Right, this is going to cause a depletion zone in this here, because if we think of this as being the diode in the reverse direction, so we're just going to create a depletion zone in this area here, and this is going to reduce the effective conducting area, because the depletion zone is not conducive to conduction, because all the carriers that are free to conduct have been pulled away. So as we increase this voltage here, this bit here becomes a depletion zone, and this is the bit that allows current to flow through this device if there was a voltage to flow. So this is the bit that can conduct. This is the bit that now can't conduct because we've pulled all the free conductors away from it. So by controlling this voltage here, we control the size of this depletion zone, and that effectively controls the width of the conducting area on this device. Okay, so small depletion area, low conductivity here. This is a conducting bit. It's quite good at controlling it, and that happens when this voltage difference here is near zero. Okay, we haven't got much negative voltage here. If we then increase this voltage, this bit, so increase it negatively, we pull all the conductors away from this area, and this is the bit that's left conducting. So conducting area has reduced, and therefore the resistance has gone up. You can't get as much current down here as you could before because the area is reduced. So in principle we can control the current by varying the voltage at this gate, but it's not quite as simple as that. This is all very straightforward, but there's nothing actually conducting through here at the moment. Right, so we need to understand what's happening when we start to make a current flow through this thing. So let's put some definitions in place first of all, just so that we know what we're talking about. We'll label our terminals. We'll call this one the drain terminal and this one the source terminal. So these are very similar to emitter and collector type terminals in a bipolar transistor. Yes, it means exactly that. And you might then ask the question, Sam, or what happens if you make the gate go positive? And that's a different ball game, and we'll talk about that going forward as well. So yes, you're getting the idea. So we've got a drain, we've got a source, we've got a gate attached to this. We define the voltages the same way as we did in the bipolar. So this is the volt of the gate with respect to the source. This is the voltage of the drain with respect to the source, because voltage is always measured with respect to something. And then we'd have ID, the drain current going through it. And these are the main things that apply to FETs. So the main voltage you have to worry about are VGS, which is the equivalent of VBE in a bipolar transistor, and VDS, which is the voltage across the device. And the only current we're actually interested in is ID, which is the drain current through here. We're not going to be interested in any currents going on over here, and the reason for that will become apparent in a minute. So this notation applies to all FETs, be they JFETs or MOSFETs, so we only have to learn it once, which is great. And now we can apply a voltage here to drive a current through here, and that gives us our ID current, and the value of this current will depend on the effective resistance of this block of silicon. Now, if we apply a voltage across the drain and the source, so apply a voltage across here, this end is obviously at V, this end is obviously at 0, and we've got a continually changing voltage all the way down this device. If we were able to break into it and measure the voltage, it's going from V at this end to 0 at this end here, which means that VGS, the voltage between here and also the voltage between the gate and the source, is effectively continually changing. Well, the voltage difference between here and here is changing continuously. So the depletion zone, the bit where there's no conductors, effectively becomes a triangle like this. So now we've got a varying area down our device, because the voltage is changing down the whole length of this thing. It's got to be consistent all the way down the whole length of this. So we've got VGS is 0 here, so we've got no difference here, so a very small depletion zone, and it's going to be much bigger at this end here, which gives us this bigger depletion zone. So as V gets bigger, this V here, so does this gradient. We pull him more away from this area. So if we increase this voltage here, that's what happens in the devices, and this area starts to get smaller. This stays the same because the voltage difference between these two is still 0. So if we now fix VDS and change VGS, so this has been fixed to the voltage, got the same voltage across here, and we adjust this one over here, we can see that an offset is introduced at the bottom, because if we change this one, so there's a voltage between here and here, then this depletion zone at this point will get bigger. Let's get bigger at this end as well. So now we've got an offset going in, so we're controlling the whole width of this thing, same as before, but this gradient is superimposed on it because we've got a voltage difference between here and here. But the net result is the same. The channel resistance has been increased because all the current is trying to get through this narrow bit, and that's the key to this. It's got to get through here before it can get to the fat bit. So this is sort of an idiot's guide to how the FET works. And then you can start to create what we would term transfer characteristics based on that kind of idea of going forward. And if we fix VDS, that's the big voltage across the device, and then vary VGS, we can see that the channel width will alter, and that will change the current flowing through it, and this change won't be linear. So here's V gate going negative, and as it gets more and more negative, we end up with less and less current being able to flow through it. And then you can see that maps over here onto the drain current, so the current flowing through the whole device irrespective of the or varied on the voltage that we find at the across the whole thing at that point. And as Sam pointed out, maximum current flows when VGS equals 0. So VGS equals 0 here, because you can see this curve emerging, you can say, well, this is the maximum current that can flow through that device. And so that happens when VGS equals 0, which is when the gate is grounded. And making the gate more negative, so if we apply a negative voltage to our gate, we get less and less current allowed through our device. And eventually you can see that if we get negative enough, we'll get to a point where no current flows. So the thing is then off. So we've got these two operating conditions now. We've got off when the gate voltage is very negative, no current flows through it, and we've got very much on when the gate voltage is 0. But you might say, well, actually, look what happens if I carry this curve intuitively, it might actually go positive. And it sort of does. And the question's been asked here, why can't the gate go positive? Well, the gate can go positive. It just, the whole thing stops operating as a transistor at that point, because if you remember, it was a PN junction. And if you make the gate positive, then it starts to go into its forward conducting region and acts like a diode. And you will just get current flowing through it like it was a diode. So we have to keep the gate negative for it to not act as a diode. So it's a diode that's always negatively biased in that respect to the gate junction anyway. And if you then fix the gate source voltage and vary VDS, we can see that the current rises with increasingly applied voltage up here. But then it'll eventually plateau out, and we'll end up with a fixed current going through the device, because you can't get any more current through the device because of the narrow width of the channel. So it gets to a point where there's a maximum current that can flow, irrespective of how much voltage you put across the thing to drive it. And we should start to recognize this kind of characteristic as a current source. It's providing a fixed current in this region here. The current is not changing, irrespective of the voltage we're applying across the device. So it acts, something a bit differently in this region down here, until we've effectively got as much current flowing through that channel as we possibly can. No more can go through, and then it flattens off and says, you can put as much pressure as you like behind me, no more current is going to flow through here. It's going to be fixed at that value there. Okay, so I think that's about all we can really say about that at the moment. So if we put those two curves together, so this, remember, is the input side curve, and this is the output side curve in terms of drain current here, controlled by or dependent on the voltage across the device, and this is the drain current that flows dependent on the input gate voltage. We get this type of set of curves where we can operate on the input side, and that leads us to this set of curves over here. So for each value of VG here, we would generate a whole curve for that value of VG as VDS varies. So the slope here is the equivalent of a resistance, which can change with VGS. So the slope of this can vary. Which mechanism makes it a constant current source? Well, the fact that you can't get any more current through it, it gets saturated. You can imagine, this is a very simplistic view, okay, that under these conditions, if you increase this voltage much, you will try and get more current to flow through this area here. But eventually you'll get to a point where you physically can't get any more current through this gap. You can't squash it through. And it doesn't matter how much pressure you put on that then, no more current will be allowed to flow. It gets the maximum. It's restricted by the narrowness of this point here. Okay, so this is a very simplistic view. And at that point you can make this voltage big if you like, and the current won't go any lower. If you turn this voltage down, eventually you get to the point where we aren't trying to ram electrons through this gap, and they can vary their flow rate then. That's a very simple view. I hope it's not too simple. Does that help, Demetrius? Right, I'll take that as a yes. No, you don't get linear relationship. It's just jammed. It's like turning a tap on. You can put as much pressure as you like behind it, but eventually it won't rise anymore. At least not very appreciably anyway. So we end up with this constant current reaching a plateau, but you get the linear region. This is, in fact, it's called the linear region down here, and that's what's going on. So this is the bit where we can control it like a normal source, if you like. This is like a normal tap controlling the current. Turn the tap on, current flows. Eventually, you can turn the tap on as much as you like. You won't get any more out. Okay, right. That's what happens. So we've got a constant current. So the important thing is to remember we've got a constant current source above a certain threshold, and below that we've got an interesting region where it's sort of turning on, but it is a more linear relationship and actually has dimensions of resistance, or dimensions of conductance in this case. Right, so this is what we end up with, and this starts to look a little bit like the bipolar transistor curves that we saw earlier in the course. Certainly for the output side, it rises up until we reach a constant current position, and that constant current is depending on the input conditions at the time, which in the case of a bipolar transistor was dependent on IB directly, the base current, which was indirectly dependent on VBE. But in this case we're saying it's directly dependent on the gate voltage, and we don't actually have any gate current because it's a reverse bias diode, remember. So we approximate that to say there's no current going into a FETS gate. Right, so these are imaginatively called region 1 and region 2. So we've got the rising bit, which is region 1, and we've got the flat bit, which is region 2. And in a bipolar transistor, it was a lot more marked. Let's get the pen up again. This is where it's going to get very messy like this. So in a bipolar transistor, it rose up really quickly and then went flat. Because this bit was exponential in nature. Here it's a lot slower rising, and that should give us a clue that it's maybe not exponential in nature as this rises up here. So we'll look at that in a bit more detail in a bit. So this is the interesting area of pinch off, when this depletion zone we've tried to get it all the way over. We've applied enough voltage so that this depletion zone would try to be completely closed off, but that's a set of conditions that's not allowed to happen. And if you look at the equations, you can probably see that, because if it's completely pinched off, no current flows, and then we've just got a big voltage drop across here. So it's sort of, there's always going to be a sort of a tunnel through here that allows something to go through. So this is the point when the value of the current is a maximum, and it turns out to be a maximum for VGS equals 0. And at that point, so at this pinch off region, the field effect transistor isn't acting as a voltage controlled resistor anymore, but is now behaving as if it was a constant current source. And so what it's saying is that through here there's a set of conditions that say the current through here is limited to a maximum value irrespective of what voltage we apply across this device. And that's when this depletion zone has been pulled all the way across, tried to be pulled all the way across to the other side of the device. So that's the nature of our JFET. There is a value of VGS for which no current will flow, and this is effectively when the channel is pinched off, and what happens in this case for VDS equals 0, or is pinched off when VDS equals 0. And this is called the threshold voltage, and this is down here. So whatever the voltage, if you apply a negative voltage to the gate of your FET, and it's below this value here, then no current flows through the FET at all under any conditions. It's off, okay, because there's just no conducting region allowed. And for a JFET, this has a special, and the other side of things is that when VG equals 0, the gate voltage is 0, we end up with this maximum current flow through our FET, because anything above that, strictly speaking, a little bit above that is okay, but we take that as the value here. But anything above that value means that the diode that makes up the junction is now going to be starting to be forward biased and will start to be conducting in the wrong direction. So this is the sort of effective maximum that we can work with. So at that point here, we've got the maximum current, and through a JFET we have a special value for that, and it's called IDSS. Usually anything that's got double subscripts like VCC, IDSS usually means it's some kind of maximum that can't be exceeded. And that's the maximum current that can normally flow in a JFET and is defined by the manufacturers by how they've made the device. So we've got these two interesting parameters for a JFET. We've got the maximum current that can flow when the gate voltage is 0, and we've got the voltage at which no current can flow ever, so the thing is off. And in between there's this sort of area of transition. So, important points to take home about your JFET. For the JFET, VGS, the gate source, is always negative or 0. With respect to the source, VGS has to be negative or 0. Maximum current can flow through the device itself when VGS is equal to 0. VGS, strictly speaking, is not allowed to go positive, and best you don't do that. There are conditions where it's allowed to go slightly positive, and we'll talk about those in a week's time or so. And the device can act as a voltage controlled resistor to first approximations for small variations in VDS when it's not pinched off, when it's operating in the slopey part of the curve. But once it's reached that threshold point and it's pinched off, the device acts as a constant current source, and the value of that current is controlled by the gate source voltage. Okay, so we have to think of it as two chunks. We've got one chunk where we're in the rising part of the curves, where we can actually treat it as effectively a voltage controlled resistor, and above that, in the flat bit, we can treat it as a constant current source, where the value of the current source is controlled by the gate voltage. And so this should be ringing a few bells in your heads to say, well, that's effectively what we said the bipolar transistor was. It was a controlled current source, and we were able to make some amplifiers from that. So we can maybe start to see that in that region these FETs will act as amplifiers, same as the common emitter and the common collector device. But although we didn't use that slopey region in the bipolar transistor because it was a bit unpredictable and a bit exponential in nature, and wasn't very big either, in the case of a FET, the slopey region is much wider and does have a relationship between V and I that is approximately linear, and so we can maybe think of some uses for the device in those regions as well, and we'll talk about those going forward. Right, how much bigger is each of the regions in relation to each other? Well, it varies from device to device, and we'll do some modelling to show that, so hold that question. So current does flow when it's pinched off if your gate source voltage is between 0 and the threshold voltage, so in that sort of conducting region. Yeah. So what you should do is probably, like all these things, you're going to have to go back through these notes at a slower rate and just do a little bit of work and try and understand it. And there are some, if you go back to the ELEC1207 notes page, which you can get to from Blackboard, there's one tab that says ECS notes page. If you go to my section there on notes, you'll find that there are some example questions, some old tutorial sheets that you can go through to allow you to develop some of these ideas and test them out. You're not going to get everything from a lecture because we get very short on time in these things. But yeah, go and have a go. In fact, you can do it this weekend probably. Have a go at some of the tutorial sheets that you'll find on the ECS notes page, which you can link to through Blackboard, and also have a go at well, you should be having a go at the coursework now as well, and that will probably help cement some of these ideas going forward as well, because we are moving at quite a fast pace, so you can't really get behind. And I said this right at the beginning. It's there's some hard concepts coming through. Okay, MOSFETs. So in many ways the JFET can be treated as a special case of the MOSFET, which is helpful because if we understand how a JFET works, then we've really got a good idea of how the MOSFET works. The MOSFET is more general than the JFET. So the MOSFET, sometimes it's called an IGFET, which is an insulated gate field effect transistor, removes some of the limitations of the JFET. we'll worry about the types of MOSFETs in a few minutes, if you don't mind, Sam. Okay, so right, so insulated gate field effect transistor. This no longer uses a PN junction at the gate, but just uses an insulating layer. So in some ways it's a simpler idea. It's more complicated to make, but it's a simpler idea to get your head around. So this allows VGS, the gate source voltage, to be bigger than naught if it wants to be, and we don't get this conduction because it's an insulated gate. And VT, that allows us to define VT, the threshold voltage, the voltage at which this thing stops conducting, can be arbitrarily designed, and it doesn't have to be negative. We can make it positive if we want to as well. So this means that we can design devices that can be controlled with both negative and positive voltages going forward. So this probably is adding something to Sam's question there. Right, so remember this was the sort of input curve that we have for the JFET, and it stopped at VGS equals 0 in the case of the JFET. Well, if we remove that restriction, because we no longer have a diode at our construction, we'll look at the construction in a bit, we can say, well, actually we're allowed to put this curve almost anywhere we like now, really. So this is the case for the JFET, and we will call this a depletion design, and the reason for the name will become apparent shortly when we look at construction of this. So this is a depletion system, and this is defined as the channel is conducting for VGS equals 0. So at VGS equals 0 here, this characteristic says there's current allowed to flow through the device, and that's the definition of it. The other type of device is called enhancement, and for that the channel is non-conducting for VGS equals 0. Okay, so we've just moved the curve up the characteristic by making it slightly differently, and now if we say that VGS equals 0, which is VGS equals 0 is here, we can see that effectively this curve is carrying on down here on the axis, and it's non-conducting. Okay, so they're the two, that's the definitions of enhancement and depletion when it comes to more general types of FET. So remember the JFET was just a one type of version of this curve where it just ran from here. So we would call that depletion type device. But now we've removed that restriction, we can put this curve wherever we like, and we've ended up with another set of conditions where once we get to the point where when VGS equals 0 this thing is not conducting, and it has to go very positive to conduct now, we can call that an enhancement device. So these are just definitions really. So this leads us to two types of device made in the way that we've been looking at the moment, and it's called an NMOS device. Device is normally on with VGS equals 0, so the same as a JFET. VG, the gate voltage, or VGS, needs to go negative a long way to switch it off, and that's called an N-channel depletion device. And in this case, with this type of characteristic, when we're allowed to move this characteristic all the way up here, device is normally off with VGS equals 0, which is here. Okay, VG needs to go positive with respect to the source to switch it on, and this type of characteristic, if you have a device like this, is called an N-channel enhancement device. So that's now we've got two extremes of device for our general MOSFET, whereas a JFET only had one device. If we make the channel out of a different material, a P-conducting material rather than the N-conducting material, everything just gets reversed. People just glibly say that. But if you look at the characteristics now for a different device that's made of P material, device is normally on when VGS equals 0. Okay, VGS has to go positive to switch it off. To get to this point here, we've got to move this way down the curve. So this is the P-channel depletion device, and likewise this one is normally off when VGS equals 0. VGS has to go negative to start to get some current flowing through it, and this is a P-channel enhancement device. So this is a PMOS type device with this characteristic. The other one was an NMOS device with the characteristic that's mirrored because it's been made of a different type of semiconductor material with a N channel. And if we combine an NMOS device and a PMOS device on the same piece of silicon, which we can do because it's at the point of manufacture, this gives us a technology called CMOS. which I imagine some of you have probably heard of, where the C just stands for complementary. So CMOS is a combination of NMOS devices and PMOS devices configured to be complementary when they operate, and we'll look at that in a little bit, how that actually works going forward as well. Right, so there's some similarities between these and BJTs. An N-channel enhancement FET operates similarly to an NPN BJT, and a P-channel enhancement FET operates similarly to a PNP BJT, where BJT is a bipolar junction transistor. Okay, so we end up in this world of abbreviations and anachronisms, and with N's and P's all over the place, and it gets very confusing. So you just have to, you just got to learn it. There's no way around that. So how can we make one of these? So the attraction of this becomes obvious when we start to see how we would make this. There's lots of complexity in the making of this, so I'm going to try and keep it as simple as we can, because we're not really into making these devices. Hopefully you're learning how to make these devices in the semiconductor course. But a JFET structure that you could make in an N-channel device is that you'd have a lump of N here. You've just got a substrate here that you're not really very interested in, so we're assuming there's not much conduction between these points. And then we've got our interesting areas for our connections of our source, our gate and our drain. And all we've done is we've made this a little bit more conducting, so it's easier to connect wires to. That's the sort of idea behind this kind of stuff. But the gate we've created out of some P+ material that we've embedded into our N-type, and then this other N+ here is really just to help us with connections. So we're going to get drain to source conduction through here, and then by applying a voltage here, we've made a little PN junction here. We could, if we wanted to, connect this around to here if we wanted to, but normally it's just connected to ground to just make this not really relevant in the circuit. It's just a carrier layer. It's physically to hold the circuit up and not let it fall apart. Don't worry too much about this area down here. Think about this bit. So we've got an N-type and we've got a P here. So this is the area where we're going to get a depletion zone if we apply a negative voltage here, and that will restrict the amount of conduction that goes on down here. The schematic is drawn like this, and you can see from this construction that it's symmetric. There is no real difference in this construction between the drain and the source. So if we've got our drain and source connections round the wrong way in a circuit, wouldn't actually make a lot of difference to the operation of this device. Now in the practical world there is a little bit of difference, because they do change this doping for very obscure reasons. But very simple devices, you can make a very simple device and you could swap the drain and source connections around in your circuit and it wouldn't make any difference to how it worked. So it's a very sort of symmetric type structure, and this is reflected in the symbol. So there's no difference between either end of these things. It just happened to be labelled drain and source, but you could swap the labels if you wanted to. The gate is the only interesting one, and depending on if it's an N channel or a P channel, the arrow on the gate either goes in or comes out. So that's how you can identify them on circuit diagrams. But we don't bother with other arrows in this part of the circuit. It's all symmetric. So it's a nice simple sort of symbol for it. So we'll talk about MOSFETs in a minute, but so JFETs always depletion, conducting when VGS equals 0, we know that. Gates of the JFET must also be reverse biased with respect to the source and the drain, otherwise we get a positive biased junction and it acts as a forward biased diode and current flows and it's no longer a transistor. This restriction does not apply to MOSFETs, where the only limit is set by dielectric breakdown, and this becomes more obvious when we look at the construction of a MOSFET. So it's the same kind of idea. We've got our substrate down here, which is just sort of carrying the whole thing. This bit up here is the interesting part. Okay, so we've got a bit of doped areas here just to help us connect connections to it. We've got our N channel that's embedded into this system here. We then put an insulating layer on the top. So we literally just put an insulating layer. It can be glass. It's labelled oxide, but glass is a good enough sort of thing. Any kind of insulator will go on there. And then we just put on an electrode, some conducting layer on top to allow us to apply electric field here, and it's labelled as polysilicon. So polysilicon is a conductor. It's not a brilliant conductor, but it's very easy to add into silicon processes, which you can just evaporate this onto the top or plonk it on the top, stick it on there. And it doesn't need to be brilliant because there's no actual conduction here. It just needs to be a bit conductive to allow us to spread an electric field across this gap. So it doesn't need to be brilliantly conductive, it just needs to be a bit conductive. And then we can apply a voltage here, and that acts as puts an electric field between through these zones here, and allows us to pull charges onto the surfaces here. And because there's no diode in this region now, because this is just an insulator, we can make the gate go positive or negative with respect to this area, and it doesn't cause any conduction through this path. There's no conduction through this path because this is just a layer of insulator. So you can see, and again, you can see a symmetric construction here in this particular simplification. There's no real difference between the drain end and the source end, and it's quite simple to actually make. It's just all to do with areas of silicon now. Now the MOSFET is a little bit more complicated in terms of its schematic. We can tell it's a MOSFET because now we've got two lines here, which is sort of telling us there's an insulating layer, and there's no real difference other than we end up with a dotted layer for the enhancement type system, and we've got a solid line for the depletion construction, and the arrow, which is normally connected to the source, to be honest, is either pointing in or pointing out, depending on whether it's a depletion or an N or a P. So again, there's all you can do is just learn these and just learn them. That's it. There's different flavors. They have to be distinguished. If you do them every day, all day, every day, you'll learn them quite quickly. So notes on MOSFETs. So you may have noticed there's a 4-terminal device, not 3. But for discrete devices, so this is devices that come in a little package, like you might be used to seeing transistors. So a package that's got. Can you? Yes, you can. Yeah, I've said that. The subject B is normally connected to the source to effectively give a 3-terminal device. So this is what happens when you make a discrete device, because you make lots of these devices on one big wafer of silicon, and then you have to chop them up with a saw into individual devices. And what you then do is you connect internally. When you buy the device, the substrate is connected to the source. So at that point, then you can't swap the terminals around. You have to get it the right way around at that point. But in a wafer scale device, so a chip that's got lots of these MOSFETs in, then there are other uses for this B pin to do with biasing, and that is something that is hidden inside the operation of a chip, and we're not going to cover that. So when you buy a device and it's just one on its own in a little transistor, which is what we're interested in, you will find that this B connection is going to connect to the source. So the B will be connected to the source in terms of the symbol. So it looks like that in all cases. If you buy these as single devices in a little can, which is what we're going to be dealing with. Right, and then we know that MOSFETs can be of two forms, depletion and enhancement, and we recognise that the definition of this comes from the construction of the device, but the definition comes from when VGS, whether it's conducting if the gate voltage is 0, or non-conducting if the gate source is 0. And to get an understanding of that, you need to go back to those graphs that defined enhancement and depletion to get an understanding of that, or why that is the case, if you want to know. And what we need to do is construct a model for our FET so we can start to understand what's going on. So this goes back to the question about how big are these regions. We can actually do a bit of basic maths to work out how big these regions are and where this join is, if you like. When can we start treating this as being flat, and when can we treat it as being in this region here? The nice thing is that despite there being several different types of FET, as we've discovered, we can use the same basic model for all of them. So we only have to learn one model, and then it's a question of getting the signs right. And what we're going to do is we're going to define the maths, simple maths for region 1. So what's the equation of this curve here? And then we're going to be looking at what's the maths for region 2, and effectively defining the equation for this curve here. And you know, they've got to join up, so that's what helps us there. So that's where we go. It's all to do with the doping on so Finley in terms of their construction, and I would ask that question to someone like Professor Gardes or whoever else is doing the semiconductor course, and they will be able to give you a much better explanation than I can. It's not really important for this course, and it'll probably get confusing. Right, so we're going to end up constructing this model because we're not actually interested in the device physics of these things. We're just interested in what are their characteristics and how can we then exploit those characteristics. So there we go. That's what we're going to be ending up with. So what we'll do is, it's a good point to stop now, is we'll stop now and then we'll look at the sums involved. Remember, this was an exponential region in the bipolar. It's not in this, so that's some ways that's nice, some ways a bit more complicated. But we'll look into that and we'll get a bit more detail of that because I'm sure you're getting a bit overwhelmed by the whole thing. So we'll stop at that point and yeah, we'll pick this up later on in the week. Okay, so bye for now.
Thanks,